when you recently I have discussions, and somebody asked me, what happens when you shine laser on this, and go and watch YouTube.
Exactly.
It's on SPICE. It's on SPICE talk of Dmitry Afanasiev. Just open that talk.
Exactly. So I think, but you can also go on. We have them all linked through our website. So if you go to the.
Sure.
So this is actually one thing that works pretty well. Let me actually now share this right here. And 1 second, I'm gonna just to be ready because I tend to be right on time a little bit. Very good. Let's see, I have to check my official time. Okay, so I think this is the official starting time. So I'm going to start if you don't mind. So I'd like to welcome everybody back to this SPICE-SPIN+X online seminar series that we start again in the fall. For us, we tend to start a little bit later than the US side because our semester starts now. We had a little break during the summer season with a lot of workshops. I organized this together with Libor Schmekiel, Angela Wittmann, Karina Vesosete in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center, led by Martina Schliemann, Borja Hillebrands, and Matthias Chloe. I think by now everybody that is signing in knows that this is a Zoom webinar, so you see the speakers and nobody else around, unfortunately, it's just to avoid any conflicts. We do have next week also a person lined up for the discussion, and then I'm going to be contacted with quite a few people to pile up to fill up the schedule. So please be paying attention if you have any suggestions, please contact me. Today I'm very happy to have Branislav and Nikolić here. We actually started together a little bit at the same time our careers. He ended up in the East Coast in Delaware. I was in Texas, but after he finished his PhD, joined Delaware, where he's a full professor for a long time now, almost 20 years, I think. And then we had actually worked together at the beginning of that. I think on the work on the spin Hall effect, but he works a lot on non-equilibrium phenomena and quantum mechanism systems, particularly bring into this multi-scaled modeling that is very important to at least to battle something that one of the hardest things, which is interfaces. So with that, I'm going to stop sharing, and I'm going to ask you please to go ahead and share your slides with us, and start anytime you want.
Okay. So you can see the screen?
Yeah, great. Thank you.
Okay. Yeah, so many thanks for these invitations, and thanks to the organizers for keeping this tradition alive. As we just discussed, these days you have some discussion in Spintronics or Magnonics, and instead of doing the old-fashioned way, pointing your students or colleagues to research paper where you would find more details, you could tell them also go to the SPICE seminars website and take a look at the talk of specific person, and you will find all the details there. So it has been a great collection and addition to the literature. The most important item on this first slide is actually the website of my research group, on which you can find a publication link. And if you see any red reference or a red item on the slides in red ink, then you can quickly go to this website and get the PDF without drilling through publisher websites and doing proxies and stuff like that. You can also scan it with your phone, this QR code, and get there quickly. This research has been supported by NSF, National Science Foundation in the United States, for the past 6 or 4 years, and the past 3 years it has been supported by this nice MRSEC University of Delaware Center, which has 2 units, and one of these 2 units is heavily focused experimentally on the topic of ultra-fast light-driven magnetic materials and many other topics within spintronics, magnonics, and quantum science in general. And let me also mention that we are just starting the search for new experimental condensed matter faculty focused on quantum coherence, entanglement, and quantum science in general. And the ad will be available shortly, and you can also email me if you're interested and have any questions. So regarding the title of the talk, since SPICE seminar organizers, when they do it in person, like to go and put the events into these nice wine cellars in Europe, I could actually rephrase this as something like old wine, which would be spin pumping, because spin pumping has been around for at least 2 decades, since the seminal paper in 2002 by Bratas, Bauer, and Cerkovniak, when they introduced all the major concepts. And that old wine is going to be put into new bottle stock, which is old wine will be put into new bottles in this stock, which is Terahertz Spintronics, which mostly means some ultra-fast light-driven magnets, or also Terahertz-driven antiferromagnets. And you will see that there's some kind of interaction that eventually these new bottles can change wine. Maybe that doesn't happen with real wine, but you can change the wine from the barrel or something like that. So let me start by acknowledging my collaborators, which is my graduate students currently in the group, then my former postdoc, Kapil Delouis, former postdoc Marko Petrovic. We have excellent collaboration with Professor Feiguin when it comes to using different many-body algorithms. Somewhere at the end of the talk, I will switch from single particle description to a many-body one. And then experimentally, we talk a lot with Professor Benjamin Jungfleisch in UD Mercek. During the COVID lockdowns, you know, we were watching SPICE seminars and reading all kinds of stuff, and ran into this essay saying scientific paper is obsolete. And what it really means is that it is not the paper as a concept that we transfer the knowledge most easily, and the latest stuff is always in the papers, not in the books, not in the review articles, book chapters, and so on. But what they really mean is that paper as a medium, you know, the one invented by Chinese papyrus, might be old-fashioned, and by the same token, talks might be kind of also old-fashioned if you're just showing static slides. So they mean, like, you know, maybe you should give your participants Mathematica notebooks, Python, Jupyter notebooks, Julia, and that kind of stuff. So I cannot do this here, but what is going to be a helper on the top of static slides is going to be movies. So as we go through the slides, please watch the movies carefully, because they can clarify many things, even if maybe some concepts are not completely clear for non-specialists in this field. So what is the main topic of Terahertz Spintronics? Well, the main topic, one of the main topics, has been since 1990s to take an ultra-fast laser pulse and hit a ferromagnetic layer. In the beginning, it was just a single ferromagnetic layer, like iron, nickel, cobalt. And what happens then is that you would get a change in magnetization. And that change in magnetization is called ultra-fast demagnetization. It basically signals that you're pushing your magnetic material very far away from equilibrium, and its properties are then quite different from standard magnets in spintronics, magnonics, which are kept near equilibrium, some kind of linear response regime. All kinds of processes could be done much faster. Switching, there is a nice review article by Alexei Kimmel about this. And on the top of it, it was observed already in early 2000s that these magnets, which are pushed into this far from equilibrium regime and have this demagnetization dynamics, they also radiate. And what do they radiate? They radiate extra radiation, which is in the terahertz range. And naively, you would expect that this radiation would be of the so-called magnetic dipole type. There is a typo here. This is taken from this reference, so I think it's a small typo. It should be delta T square M over T, but this effect is actually very small, because anything that has to do with magnets, when it comes to emitting electromagnetic radiation, generating electromagnetic field, is 1 over C. small because magnetism is relativistic effect. It does not exist in a universe in which speed of light is infinite and speed of light is quite large. So like in fact in this formula you would see in this proportionality sine 1 over c cube. So like we have been checking this and it's really tiny compared to other important stuff that you're going to see. So in any case, experimentally, it has been noticed that any kind of radiation coming from this single ferromagnetic layer is 100 times smaller than any terahertz radiation that would come from new kid on the block, which is what is happening in the past 5, 6 or so years, that you add another layer of normal metal next to the ferromagnet. You still pump with a femtosecond laser pulse. Typically, community likes to use 800 nanometers wavelength. And then what you get is also terahertz radiation, but now the terahertz radiation in electrodynamics terms comes, at least intuitively, perception is it coming from some kind of charge current changing in time. And this is a much stronger radiation, 100 times bigger than the one observed in early 2000s. And that then makes this both spectroscopy technique, because by measuring terahertz radiation, you could try to infer what is happening in this bilayer, and it becomes a applied device because you could have a very good spintronic terahertz emitter. Here is a comparison of the spintronic terahertz emitter versus standard semiconductors. One of the major advantages that you find out, as discussed in this nice Nature Photonics review article by Matthias Chloe and others, is that you have a broadband radiator instead of having, for example, this semiconductor terahertz emitters, which emit in some range of terahertz frequencies, then there is a gap. These spintronic emitters are broadband. You can tune them in various ways. For Spintronics community, aside from these applications, what is important really is to understand where is this charge current that radiates, time-dependent charge current, coming from. So a standard notion is that this magnetization that is moving is basically emitting or pumping, in the language I'm going to use, spin current, generating spin current, and there are all kinds of mechanisms intuitively proposed, but in this talk I'm going to try to put this on a firm microscopic ground, at least for some examples of magnetic materials. And once that spin current is generated by whatever is the microscopic mechanism, then there will be spin to charge conversion. And that by itself can be a complicated process because you could have a backflow and all kinds of charges which are changing. And I will show you that that can be also very important due to the structure of solutions of the Maxwell equations. So in any case, the spin current by itself is very important quantity. And for example, some of the mechanisms that have been discussed in the literature would be inverse spin Hall effect, Edelstein effect, which is the interfacial one. Then there could be anomalous Hall effect from this recent PR applied. And also Comfort Group has discussed in this advanced material that you could have skew scattering at the interface. So basically, whatever you see in other fields of spintronics, such as spin orbit torque, it almost looks like, and there is a connection. If you see spin orbit torque by any of these four mechanisms, for example, you could see this spin to charge conversion in these ultra fast driven heterostructures. So another topic in terahertz world of spintronics would be terahertz radiation driving antiferromagnets. By the way, if you go to the previous page and you try to drive terahertz by terahertz electromagnetic radiation pulses, the same bilayers, you do not get terahertz out, according to discussions with my experimental colleagues. So this is also like something to keep in mind as a puzzle for theorists. So in terahertz driven antiferromagnets, which experiment started by this for the first time by this Nature and Science paper, Science is by Del Barco group, you're basically driving antiferromagnet into dynamical precession of its localized magnetic moments on two sublattices, and then you end up with a spin pumping of a similar kind as the one you have seen in this theory from 20 years ago and numerous experiments, but now it is the antiferromagnet which is driving the pumped spin current by dynamics of its local magnetic moments, and everything happens at a much higher frequency, which is 0.5 terahertz in these experiments, or 1 terahertz, and so on. So then comes the question of how you understand all of this phenomena. On the second slide, I show you of ultra-fast driven ferromagnets, and it turns out it's extremely difficult problem because there are many competing mechanisms. The system is far from equilibrium, and these mechanisms are actually kicking in. Maybe on the first 10 femtoseconds, you have one mechanism, and then in the next 10 femtoseconds, you have another one. And this is what makes it very complicated, because whoever wants to write a Hamiltonian and makes this microscopic description and calculation would have to put all of this stuff together, or it would have to start from some powerful first principles method that can capture this. So there are phenomenological theories of this phenomena, such as Peter Oppener's group superdiffusion. People have been using Boltzmann equation, Vlasov equation, plus LRG equation. This would all be like semi-classical description. Then there is a fully quantum description, a microscopic one, when you start from some Hamiltonian, and then you try to decipher what happens once you hit that Hamiltonian and introduce laser light into its hopping matrix elements. And this paper is particularly important for the rest of the talk, because we are going to be using very similar formalism, but with a twist of Lindblad quantum master equations to evolve these electrons hit by light. And then there are first principles calculations that could be, in principle, the most detailed. And indeed, if you open some of these papers that I have listed, they have provided a wonderful insight. For example, here you can see just a nickel dimer hit by light. And then you can see how the angular momentum is transferred from electronic subsystem orbital to spin to ionic orbital. All of this stuff is labeled if you open the paper and read it carefully. There's a total one here and so on. So it's a beautiful insight on a very simple example, and I'm going to use these simple examples throughout the talk as well. Then you can see, for example, that using the bulk material is not the same as using the slab. So this is actually telling you what the chairman mentioned. Interfaces could be very important, because once you have a slab, the interfaces are speeding up the magnetization process. There is a very nice and recent paper with a lot of new insights in using TD-DFT codes from Peter Oppener's group. And finally, the paper which I find very important is this Nature from 2019, which can show you exactly what I mentioned. For example, here what you see is experimental results. Then you see TD-DFT theory, when spin-orbit coupling is turned off, and so theory matches experiment. Then the spin-orbit coupling is turned on, and theory continues to match experiment after 10 femtosecond. But what this is telling you is that in the first 10 femtosecond, spin-orbit coupling doesn't play the role. And that's a beautiful example of what I explained, that you could have these different physics mechanisms turning themselves on and off depending on a time scale. And one of the tricks that you see in some of these papers is that you can actually decipher who is doing what by turning off specific mechanism. For example, in this paper, they turn off coupling to magnetic field, and they see no change. And then the conclusion is that if you couple light to these magnetic materials, you can forget about magnetic field again, because it is 1/c effect in the formulas. You only have to take care of the electric field. Eventually, they end up by doing the same process, figuring out that it's very important what kind of initial spin disorder is present due to, for example, thermal fluctuations and so on. One thing which is missing in all of these calculations, however, is nobody calculates emitted radiation. And modern physics is, operational science. You have to kind of always think what is measured. Time is what you see on the clock, and quantum mechanics is all like, what can be measured in the lab, as opposed to thinking what the particle has as some kind of independent property. And all the experimentalists rely on looking at this Terahertz signal and then trying to invert that signal into explanation what is the cause of the signal. And so it would be very useful then to take any of these theories and couple it to Maxwell equations and solve that to find out what is the outgoing radiation. So in particular, there are some newer examples of antiferromagnets being plugged into the same business. In that case, it's not exactly obvious why would they pump spin currents after hit by light and emit this Terahertz radiation, but the result is exactly the same, such as in this Nature Physics 2021. This is nickel oxide in contact with platinum. You have to use the second layer as some kind of spin orbit material. Could be heavy metal like platinum, tungsten, tantalum, and so on. It could be topological insulators, some of the 2D materials which have strong spin orbit coupling depending on the layers, and there is a same story of Terahertz radiation coming out. There is also this APL, which has used Mn3Sn, which is one of these beautiful Weyl antiferromagnets with non-collinear arrangement of its localized magnetic moments, and we actually have the data in the MRSIC from Jugendflash Lab, which was the motivation for us to focus on this system as an example on which we are going to tailor and tune our theoretical machinery. So here is the setup that is going to be kind of drilled through at least half of the talk. The femtosecond laser pulse comes in. Here is the layer of Mn3Sn, described by some Hamiltonian microscopic one. The one we are using was derived by Leon Balens in one of the PRLs from a few years ago. And then we can add a layer of spin orbit material. We label here in this schematic view all possible currents. For example, you could have a charge current flowing in this direction through Mn3Sn. You could have spin current. You can have spin current and charge current flowing from Mn3Sn into platinum. And then the 5 and 6 current would be charge current and spin current flowing vertically through platinum. And all of these currents can be calculated and will be calculated eventually throughout the talk. And now comes the first movie. So I'm going to run the movie, and hopefully internet is fast enough that you can see it. So when I start the movie, you see that the line is moving, and here is where the pulse kicks in. So the pulse is now in because the line, yellow line, goes through the light pulse. And you see that as soon as I am at the edge of the pulse, I'm generating current. So some of these currents that I labeled in the schematic view are here. You can see them here, and you can see how the magnetization changes. So this is an antiferromagnet. Initially, if you achieve a proper equilibrium state, you should see zero magnetization. But of course, zero magnetization equilibrium does not mean that it has to be non-zero out of equilibrium. In fact, most of antiferromagnets will develop a non-zero magnetization out of equilibrium. And here you see exactly that in this panel, that there is a non-zero magnetization forming in the course of time because of these dynamics generated by electrons being coupled to light. And if you also watch this movie again, I'm running it for the second time. As you can see from the bottom, you see that currents are being generated, but these local magnetic moments of Mn3Sn are not really moving immediately. They kind of start moving much later, like light pulse might be over, and they're moving because they live in a different world on a different time scale. So they're kind of slower. And if you get to this website that I mentioned with the which has all these red references, you could download a couple of other movies, in which case we split the movies into the period before the light pulse, during the light pulse, after the light pulse. One of the reasons why we have a movie before the light pulse, because before the light pulse, everything has to be static. And if you run this calculation that I'm going to show in a moment, you don't get anything static in the beginning because you couple electrons to these local magnetic moments. Electrons have a temperature, and then you have to equilibrate the system, and you have to equilibrate it in such a way that at the end everything is static. And we demonstrate by movies that the procedure is correct. So we first equilibrate, make it completely static equilibrium, then we fire the laser pulse, we see what happens during the laser pulse, and then we see what happens after the laser pulse. And here I could show you only one of these several movies that you can download from the website with all these red links. So what is the radiation? So now we actually came up with the idea how to calculate this radiation relatively painlessly without going into like all the tricks that electrical engineers have. Usually electromagnetic radiation is calculated, so in a sophisticated way, in a complicated geometries. In a simple geometries, you do it in your electrodynamics course and your undergraduate and graduate students. But if you want to do radiation calculation in complicated geometries, in a complicated situations such as like this, you would have to resort to something called FTDT, finite difference, time difference, different ways of solving numerically Maxwell equations. They actually bypass this, and I will show you how. So the end game is that once we couple calculation of emitted radiation to the computation of currents that you saw in the panels of that movie, we do get that in the frequencies of the laser pulse, we have high harmonics. And this is something that is extremely popular topic in dealing with, for example, topological materials. Many times or this, you can probe what kind of material and symmetry you have by firing a laser pulse and observing these high harmonics, because in one situation you would get only odd ones, in some other situation you would get even ones, in third situation you would get both odd and even, and then there is even a fractional harmonic, which means you get a peak at half of the frequency or 3/2 of the original laser frequency. Here we get relatively simple picture of harmonic at each frequency, and this would be like, 800 nanometers wavelength, 400 nanometers wavelength, and so on. This is typically not probed by Spintronics community, but it could be interesting on its own. What Spintronics community probes, and that's why the top row of panels is focused on that range, is, as we discussed, terahertz radiation. So here is how the terahertz radiation looks like out of this bilayer when everything is connected and calculated together. And you see that one other thing that we do in order to decipher who is doing what kind of job in this whole story, we are playing with these knobs. So since we have Landau-Lifshitz-Gilbert equation available to move these localized magnetic moments of M and 3SN, we have spin orbit coupling from this second normal layer. We can turn them on and off. So if we turn off LG dynamics, which means local magnetic moments, localized spins of M and 3SN do not move at all, and we also turn spin orbit coupling off, we actually get a very small contribution to terahertz radiation. And moreover, if we turn on the spin orbit coupling inside the M and 3SN, it's even smaller. And you can see this as a gray curve on all of these panels. So like somehow the spin orbit coupling, that's the conclusion of M and 3SN by itself, plays a role which is stronger than the spin orbit coupling of the second layer. Then once we turn the Landau-Lifshitz-Gilbert equation on, then we start seeing much bigger signal in the terahertz range. And this is basically telling you that somehow whatever is the terahertz in this system emitted has to do with the motion of localized magnetic moments. And so the picture, together with these pictures of local or total, actually in this case, spin and charge currents that we calculated before we plugged them into the solution of Maxwell equations, is that a laser pulse excites a photocurrent. That would happen in any system, solar panels on the roof of your house and stuff like that. This photocurrent of excited electrons then propagates through the environment of localized magnetic moments. If all the localized magnetic moments are parallel, as it would be the case in the ground state of ferromagnetic material at zero temperature, you're not going to get anything, because these localized magnetic moments spin polarized electrons in the direction of themselves, and there is no any kind of opportunity to dynamics, because torque is zero, taking into account that spin transfer torque is always proportional to expectation value of electronic spin times this localized magnetic moment. So if you have like these two vectors being parallel to each other, there is no dynamics. But if the localized magnetic moments are not parallel, and this is exactly what they discovered in this TD-DFT paper, sort of by doing this game of turning on and off different processes, then in M and 3SN, of course, they're not parallel, because there is this special arrangement of these localized magnetic moments in non-collinear pattern. Then the localized magnetic moments are going to polarize electrons in one direction, they would impinge on another localized magnetic moment for which this torque as a cross product is not equal to 0. And once they exert torque on the localized magnetic moments, they start moving. And that's exactly what is this motion of localized magnetic moments that we allow in panel B. And that motion somehow generates charge current or spin current converted into charge current. At this point, it's not clear, and that's the rest of the talk is to clarify that radiates the most into this terahertz domain. And you can see that turning on the spin-orbit coupling from the second layer does not actually improve the result. So it looks like that most of the radiation of in the terahertz frequencies range in this specific example of Mn3Sn comes from Mn3Sn itself. You don't need that second layer. This would be kind of fifth mechanism to have this terahertz emission from ultrafast light-driven magnets. There was a nice pressure by the sort of referee on this paper who asked us, nobody calculates efficiency, and that's kind of easy once you have all this machinery, because if you have electromagnetic field computed, you just get the Poynting vector as E cross B, and from the analysis of the fluxes of Poynting vector, incoming flux and outgoing flux through the whole sphere around this material, you can easily find the ratio of the two fluxes of input-output Poynting vector, and the efficiency turns out to be rather small. It's like what you see here. It could be tuned, it's not more than 1%. It could be tuned by changing the intensity of the laser beam. We can also calculate the full radial dependence in theta and phi of the emitted radiation. One important thing to keep in mind also for the next slide, and proving a highly non-equilibrium state of these light-driven magnets, is that if we actually plot instantaneous eigenenergies and eigenstates of this light-driven system as it evolves in time, and then we compare them to the standard eigenenergies and eigenstates of the Mn3Sn Hamiltonian in equilibrium, the difference can be more than 100%. And this is a quantitative explanation of how the system is pushed very far from equilibrium, and you cannot think about it using the band structures, density of states, and all kinds of properties that you regularly compute on these systems in equilibrium. And so this issue that eigenstates are changed dramatically and eigenvalues will be very important for the next slide, which tends to be a dense one and maybe a bit frightening if you're experimentalist. But the most important thing is just explain how we obtain this emitted radiation. So basically, we evolve electrons using quantum transport via quantum master equation of the Lindblad type, very similar to what Mertig and Heng did in that new journal of physics I mentioned a few slides ago. Then we obtain the density matrix as the most important quantity in non-equilibrium quantum statistical mechanics. Like, in regular quantum mechanics, you would write expectation value of spin operator of electron would be, for example, psi, h bar half, Pauli matrix sigma, psi, but this is not good for doing research in non-equilibrium physics because you have to take into account non-equilibrium, bias voltage, light, finite temperature. This is why we have to shift and use the non-equilibrium density matrix to get this S, which is trace of rho non-equilibrium, Pauli matrix here, h bar half if you want to have units. And this is precisely what we get in this side of the loop. Once we get this non-equilibrium spin density, that goes into our G equation to jerk these localized magnetic moments. The localized magnetic moments are updated, and then they introduce essentially a time-dependent field in the electronic Hamiltonian on the top of light. So light introduces time dependence in the off-diagonal elements of the Hamiltonian. The time dynamics of these localized magnetic moments is introducing time-dependent field in the diagonal elements of the Hamiltonian. And this kind of scheme, which you could call quantum classical, is very common in, for example, biophysics, chemical physics, when they have to evolve light electrons and light atoms using quantum physics, and then the heavy ions are evolved using some classical equations of motion. So here the heavy guys are localized magnetic moments. We assume you can use Landau-Lifshitz-Gilbert equation, and then everything has to be coupled in this self-consistent fashion. Once the currents are calculated, then instead of sending them into some kind of complicated scheme of solving Maxwell equations on a spatial temporal grid, we actually use something which is rarely discussed in standard undergraduate and graduate courses of electrodynamics, called Yefimenko equation. So this fellow Yefimenko figured it out, and there was a long history of attempting to write correctly these equations in physics, even before Maxwell, and debates, what is correct, how do you generalize, let's say, Coulomb's law and Biot-Savar's law to properly time retarded solutions. So he figured out how to take essentially what we usually see as vector and scalar potential and write immediately E of RT and B of RT with proper time retardation, because all of these times here are TR is T minus R over C, and R is observation point. So there is always proper retardation due to finite speed of light. And the nice thing about this equation, it gives you a rigorous way to think what can contribute to the emitted terahertz radiation, such as that time-dependent charge, derivative of time-dependent charge, and derivative of time-dependent currents, charge currents, all contribute to radiation. And you have to take that into account if you want to understand what is happening in those experimental systems. And there would be a fourth term, which comes from that magnetic dipole changing in time, which is a magnetic dipole, in this case, comes from quantum mechanics, not the magnetic dipole that you see in textbooks on Maxwell electrodynamics. So that one would be delta M over delta T squared, as was shown on that previous slide, also retarded T minus R over C, but it has this 1 over C cube in front of this expression, and that makes it very small. So in all of the testing we have done, this term is actually irrelevant. You really have to pay attention to these three terms that you see in the Yefimenko equations, and then see which one is the best contributor to the outgoing terahertz radiation. So the whole story was that these magnetic moments, as you saw from this slide, they have to move. This is what happens in this panel B in order to get sizable terahertz output. And magnetic moments moving, the simplest example of that happens in the standard theory of spin pumping is the famous concept introduced in early 2000s, which is that if you have just a single ferromagnetic layer and you make its magnetization to precess at the ferromagnetic resonance by absorbing microradiation, you're going to see that once you attach to it normal metallic layers, that precession of uniform magnetization is pumping. Pumping means current is generated in the absence of any bias voltage. A fast precessing spins into the normal metal. Eventually, these transverse components die out and the Z components remains. And you can observe this by noticing that FMR line width is changing, increasing, because you're losing angular momentum. Loss of angular momentum means more damping. And that's why you see that in this case, permalloy has narrower FMR line width than permalloy in contact with platinum. Later schemes have detected the spin current pumped into the normal metal directly using inverse spin Hall effect. So the whole phenomenon is also closely related to charge pumping that has been known since 1990s in the so-called mesoscopic and later nanoscopic physics. What happens in those systems, you have, for example, quantum dot, you attach two time-dependent voltages, you make those voltages out of phase, cosine omega t plus phi, that's why there is a phi labor here, and you would see a charge current flowing through the quantum dot, even though no bias voltage is applied. And the connection between this problem and the one here that Cerkovniak, Brates, and Bauer realized in early 2000s is that in the case of magnetization precession, you also have two parameters changing in time. These are exactly these two magnetizations in the plane. And then you can literally take the formulas from this charge pumping business, plug in these two time-dependent components of magnetic field, and you would get the spin pumping formula with famous spin mixing conductance, and so on. However, one thing which is missing in the whole story, and that was already known to them in this RMP from 2005, is that if there is a spin-orbit coupling, strong spin-orbit coupling present directly at this interface, then all of their theory is not immediately applicable. One other thing to mention, I remember in 2005, we go to some big Spintronics conference, the spin pumping theory was very new, and many students were asking, how is it possible that this fully quantum coherent theory of charge pumping can be transported into Spintronics at room temperature? For this to happen, this quantum dot has a 1 micron size, has to be cooled typically to 1 Kelvin, so that this 1 micron is smaller than the so-called dephasing length. While in Spintronics, you observe the spin pumping regularly at room temperature. And the catch is that most of the spin pumping is actually confined to the interface. And since interfacial region could be just 1 nanometer or so, even at room temperature, this is much smaller than any kind of dephasing length. So in other words, whenever you have processes at the interface, you have to use quantum mechanics and quantum transport theory, even if you're operating at high temperatures when naively quantum coherence would be lost. And so the simplest example to actually understand pumping, because if you look at these formulas that lead to spin mixing conductance, they're kind of scattering matrix derivatives and so on, is to take a friendly example from elementary textbooks on solid-state physics, which is 1D tight binding chain. So imagine you have a 1D tight binding chain, and in the middle of the chain, you put a single precessing classical localized magnetic moment, and then you ask yourself what will be the result of this precession. And it's very difficult to answer this question straightforwardly because we don't have a good intuition about time-dependent quantum mechanics. Maybe we have seen some perturbation theory and stuff like that. Even the classical physics, by the way, would be quite difficult. I give you 3 particles and I ask you what would the 3 particles do once you release them, and if they have chaotic motion as they typically have, you would have very difficult time to predict what would they do after sufficiently long time. But in this case, there is a catch. You can write this time-dependent Hamiltonian of 1D tight binding chain with the precessing localized magnetic moments, and then you can kill that time dependence by going into the so-called rotating frame. So you perform a unitary transformation of the whole time-dependent Schrödinger equation. And once you do that, you will end up with a static Hamiltonian, which does not change in time. Everything is frozen in terms of this black vector not moving. And the time derivative here gives you extra term, which is a kind of Zeeman splitting. So the end game is that this device, which used to be time-dependent, is now split into a time-independent transport problem in the rotating frame, in which it looks like, because of this h omega half sigma z term, that it's leads, semi-infinite leads, because to handle the, you cannot take in infinite infinite 1D chain means infinite times infinite matrix, and we cannot handle that either analytically or in the computer. Instead, we cut this into middle part, and then the rest of the semi-infinite parts are taken into account to something called self-energies in Landau-Boutiquier or Cavendish transport theory. And these semi-infinite leads and the self-energies are now spin split. So it looks like they're half metallic ferromagnets, and what used to be frequency of precession is now bias of chemical potential between each 2 pairs of leads. And now you see very clearly that spin down would like to go from left to right. Spin down would like to go from left to right. And this is exactly counterflow of spins into opposite direction. There is no charge current, but there's going to be spin current. There is actually a third one, which goes from the lead at a higher chemical potential to the lead to a lower chemical potential. So if you sum up these 3 terms, you get a pump spin current. And that's exactly the spin current that you would get simply by taking Landau-Boutiquier theory, which today you could do with quant. You take quant and you calculate transmission from right down to left up lead, left down to right up lead, left down, left up lead, all these spin split leads. You sum up this 3 transmission function that quant will spit for you, and that would give you the spin current without ever doing any time-dependent calculations. And if you perform this calculations analytically, let's say using Mathematica. For 1D chain, it can be done without quant. You can simply plug everything into Mathematica and shuffle through about 10 or so lines of Mathematica. You would get analytical expression, which looks exactly the same in terms of major dependencies as the ones from Bratte-Sterkovnjak-Bauer theory. Pumped current depends on frequency linearly, so that's why it's called adiabatic pumping. It depends on sine squared theta, where theta is this angle of the conal precession that experimentalists control in the lab by the input power of their microwaves, and then there's all these dependencies on the model itself. So if the system is completely symmetric, this formula has extra information compared to standard spin pumping theory. If the system is completely symmetric, you see identical spin current left and right. If the system starts to be blocked by one of these barriers, for example, the right current gets completely shut down, and the left current, naively, you would think since you shut it down on the right, it should be 2 times larger on the left, but quantum mechanics says it's 4 times larger. So this is the job of theoretical physicists, to collect all these factors of order 1 and get them rigorously computed. The new information, which is not possible to get from standard scattering theory of spin pumping, spin mixing, conducting, and so on, is that if you have this asymmetry introduced by this barrier, then you're going to get extra charge current pumping at omega square level, which is non-adiabatic effect. And so, sadly, this is such a beautiful picture, and it makes you feel like finally understand where is the spin pumping coming from. But if you introduce spin orbit coupling into the green region, then everything falls apart. And the reason why it falls apart is that if the spin orbit coupling is present in the green region, once you go into rotating frame, the magnetization is static, but spin orbit coupling becomes time dependent. And then you gain nothing, because the goal was to go into the proper frame when everything would be static, problem of quantum transport. And for that purpose, you would have to shift to bigger guns. For example, this is again a simple example, 1D chain with many spins and a spin orbit coupling in between the links of the Rashba type. If you do not have spin orbit coupling, you get this Z current, which is DC, exactly following the formula on the previous slide. The charge current is 0 if everything is symmetric. But once you turn on the spin orbit coupling, the Z current becomes time dependent, and you get time dependent charge current. So there is a completely new story because of the presence of the spin orbit coupling. There is another movie which explains what is going on and where is this coming from. For example, in the absence of spin orbit coupling, the vector of expectation value of electronic spin is nearly follows, even not completely. There is never kind of complete overlap, some kind of magic adiabatic limit. But once you turn on the spin orbit coupling, this vector is always misaligned, and it's also nutating around the black vector of localized magnetic moment, and that basically then leads to this currents. If you Fourier transform these curves that you see here oscillating in the presence of spin orbit coupling, you would actually get high harmonics. They go all the way to like 10, 20. And this is kind of somewhat surprising because high harmonics typically are obtained in intense laser beams hitting different kinds of materials having nonlinear effects. Here you actually have a very low power business, just microwaves, you know, much lower power than laser beam, but you still get business of high harmonics due to these processes here. It is possible to generate these high harmonics precisely without running fully time-dependent calculations that it was done here by so-called time-dependent Cavendish green function formalism. You can simply switch to the so-called Floquet Cavendish green functions. And with these green functions, then everything becomes time-dependent, but the matrices are infinite. You can actually shuffle them through this algorithm that was never clearly explained in the literature. We put it out in this 2023 paper, and you could basically even couple it to quant. And with this kind of equations plugged into quant, you could be able to do your own calculations of any time-dependent quantum system driven by harmonic perturbation. And the new thing is that you can get not only the DC current, but you can also get all these high harmonics. So all these high harmonics would be spit out by these formulas. And so the spin orbit coupling plays a key role in all of the stuff I discussed, for example, in the previous slide. It completely changes the picture of ordinary spin pumping. Once again, the reason why it's so different because spin-orbit coupling is now spread out through the pumping region. And, spin-orbit coupling is a kind of Zeeman term when the magnetic field is momentum dependent. The standard example to introduce it quickly would be the Rashba spin-orbit coupling. If you have, again, that 1D wire with no spin-orbit coupling, you have two spin-degenerate parabolas. With magnetic field, they split up vertically. With Rashba spin-orbit coupling, they split up horizontally. You rotate this around the z-axis to get into 2D, and you get these two paraboloids. You cut paraboloid by Fermi energy plane, and you would have this spin momentum locking, which is telling you that if momentum is here, spin has to be down, and so on. And so why is this important? Well, it turns out that you often encounter even this Rashba type of spin-orbit coupling, which look like a textbook example in real materials. For example, here is the example of cobalt, alone in vacuum, but cut into half. If you scan the spectral function of that cobalt, the surface, exactly what ARPES and spin ARPES would do experimentally, here we're doing it theoretically, what you would see is that this is the spectral function of cobalt, and the spin texture is two circles, exactly like Rashba spin-orbit coupling. So in other words, cobalt on its own, without any other material, on its surface starts harboring Rashba spin-orbit coupling because the system is inversion symmetry broken. If you cover it with topological insulator, then everything changes. You go from this spin texture to this spin texture because now the topological insulator is introducing its own spin momentum locking on the surface of cobalt. And in 2016, we ran into a nice talk by Dan Ralph, and he said, theorist, can you calculate spin mixing conductance of ferromagnet TI interface? And the reason why this is difficult, first of all, cobalt by itself, due to inversion asymmetry, would have some spin-orbit coupling at the interface. And second, if you cover it with topological insulator, it would be extra spin-orbit coupling. And as I told you in that RMP from 2005 by Cerkovnjak, Brates, Bauer, they understood already at that time that once the spin-orbit coupling is present, it's not going to work to plug into scattering matrix formulas and get spin mixing conductance. One way to see why spin mixing conductance is not applicable, so this is kind of invalid once you have spin-orbit coupling, is that spin mixing conductance formula from RMP 2005 takes into account only reflection matrix elements up, up, down, down. But in the presence of spin-orbit coupling, you would have R up, down, R down, up. So you would kind of have to derive another formula that would have 4 different kinds of reflection matrix elements, and that has not been done. Nevertheless, if the pumped current changes as theta square or psi theta square in some low range of theta angles, then you can pronounce that whatever you calculate as a spin current by some other machinery, such as this Floquet green function formalism, is the spin mixing conductance. That's exactly what we did for this Del Parco experiment. We took MNF2. You see MNF2 has a nice big gap, but once you cover MNF2 with platinum lead, for example, it would completely change. So the gap is at least near the interface closed by evanescent wave functions. This is what you see here, MN1, MN4 layers. And you also see spin textures. So MNF2 is now acquiring spin textures from this proximity effect due to this platinum next door. So as long as this angular dependence of spin currents that we calculate using Floquet green function formulas I showed you in the previous slide, coupled to DFT Hamiltonian to take into account realistic structure of these bilayers or trilayers in this case, change as a sine squared theta, we can extract this effective mixing conductance, and you can see them here. So like the message here is that MNF2 that you study, let's say, in solid state or whatever research papers as the gapped antiferromagnetic material, which was very popular in 1990s for various reasons, is not the same material once you put it into heterostructure. There is a huge modification of its properties because of the proximity effect. It's not like a usual superconducting or magnetic proximity effect. It is spin orbit proximity effect. The spin orbit wave functions are leaking from this second layer, in this case platinum, into the MNF2 and strongly modifying its properties. So there is actually one final topic that I wanted to mention because it also happens to be leading to some kind of terahertz radiation. So there is this very nice experiment, and I'm going to try to do this in 5 minutes since I'm already like toward the end of my talk. There is this very nice experiment done by Beach Lab in which they take two magnetic domain moles and they annihilate them. How do you annihilate them? They apply magnetic field. No currents, no laser pulses, no big guns applied to them. It is simply the fact that if the two walls have different topological quantum numbers, let's say +1, -1, they can be annihilated, +-1 remains 0. And then I have a third wall, which is picking up the signal that something is bursting out of this annihilation. So this topic is extremely popular in high energy physics. They would like to know what would happen if you annihilate, for example, two magnetic monopoles. You know, we live in a very precarious world with all kinds of wars coming up on throughout the planet, but the really difficult event for the future of the planet would be, for example, if you believe in string theory, 2D brains annihilating each other, and then the whole universe disappears in 1 nanosecond. So hopefully string theory is not correct and this will never happen. But in any case, these guys have been really interested. There's this whole monograph of annihilation of topological solitons and what is the result and how to test this in solid state physics. We can do the testing using liquid crystals, liquid helium, and now magnetic materials. And the result that Beach Lab observed is you will see spin waves coming out, and they're very special because they're exchange dominated and very short wavelength, which is a kind of holy grail for magnonics, because once you have short wavelength spin waves, you could run your magnonic circuits on the scale of few tens of nanometers. And they actually explain this process simply by using MUMAX. You run MUMAX and you get something like this. So here we are running our own calculations of this TD NGF LG type, which means we run time-dependent green functions or time-dependent quantum transport, self-consistently coupled to LG equation. So it's pretty much identical to what I was using to generate that Terahertz radiation from MN3SN. The only difference is now I have leads attached to the whole sample. The current can go into the leads. I have continuous energy spectrum, all kinds of tricks. So it's a kind of like alter ego formalism. We have two kinds of this quantum classical calculations. In one calculation, we are using Lindblad master equation. If we have the leads, then we switch to Keldysh green functions. And you see, like, referee on this paper was asking us to make it really slow and realistic. So it's kind of moving slowly, that eventually these walls are performing dynamics in the presence of external magnetic field applied in this direction. And eventually they will so eventually they would the two walls would so now Microsoft is not collaborating. So the two walls would disappear. You would see this green line flat, and the rest of the okay, so he's here. So you would see the green line disappearing, which means the walls are gone. The walls do not exist anymore because most of magnetization is just parallel to the x-axis, but it never stops. There is some kind of inertia, if you want to call it, and you see this oscillation. So that's exactly spin wave. So we reproduce what Beach in his nature physics did simply by running MUMAX, that the result of annihilation of two magnetic domain walls with opposite topological charges, winding numbers, is going to be a burst of a spin wave. And from that viewpoint, there is nothing else to do. But the trouble is that as these magnetic moments, as I was showing you in the movie in the past 30 seconds or so, as they're moving, you have to think that they're going to jerk electrons. So electrons surrounding these white localized magnetic moments, conduction electrons, are quantum objects, and they will feel time-dependent potentials. And they will start moving, which is again a type of pumping. It is not a pumping of uniform precessing magnetization, but it is a pumping of, let's say, something called spin motive force, which our theory captures, but with all kinds of correction. And as the electron starts moving, they're going to pump. And that's another type of pumped current. So that's exactly explanation what we are solving. There is this master equation that contains these Keldysh green functions. Again, the key trend for anybody doing non-equilibrium many-body physics is non-equilibrium density matrix. Once you have it, you take a trace that will give you non-equilibrium spin density, you take a cross product with magnetization, that gives you torque. You can get pumped charge current, pumped spin current. This is discussed in several papers that have been publishing on this topic since 2018. So if you put everything together, it looks like as if you have arrived at a new type of LLG equation, which has a time retarded kernel, and in some limits you can expand it. It looks like ordinary one, but all the parameters are time dependent. So this is what the coupling of LLG equation to this time dependent electrons is doing. There is a very recent archive, just to address this quickly, which actually derives analytical formula using Schwinger-Keldysh non-equilibrium field theory that actually matches these numerical results almost precisely. And the fundamental reason for all of this stuff, let me now give you kind of physical picture, akin to Feynman, who would write, 10,000 lines of calculations. Here we have 10,000 lines of codes, is that spin, when you have these non-collinear systems, electronics expectation of spin would be the red line, never follows the blue line. And that delay between the red and blue line causes torque, S cross M, and that torque is what you see eventually encoded by these complicated equations at the end of the day. So once you have this machinery, you can also check what is the pumped current. And it turns out that in the course of annihilation, this is where they annihilate each other, the two magnetic domain walls are going to pump spin current. And it's a very unusual and interesting spin current, because unlike the standard theory from RMP 2005, the spin current is pumped in the broadband range of 27 terahertz. And so like it is pumped continuously, like a standard spin pumping from RMP 2005 would be one frequency. This one continuously pumped from 0.3 to 27. If you convert it into charge current by inverse spin Hall effect, you would get another source of Terahertz radiation, which does not require laser beams. Okay, so I think I'm out of time here. Is that correct? Okay, so I do have 2-3 slides left of a conceptual type. Essentially, you have to be very careful when is your LLG equation applicable. What really breaks LLG equation is entanglement, Nobel Prize from last year. Once you have entangled states in your quantum magnet or any magnetic material, you cannot use LLG equation. Very recently, a nice work by my student, Federico Garcia Gaitan, we looked into this problem in detail, and we found out that almost every magnet, if you hit it with the right dissipative environment, is going to obey LLG. So like, Landau and Lifshitz knew 100 years ago, everything that we had to work so hard to understand how to evolve quantum antibody systems with a dissipative environment, Caldera-Leggett model, measured in entropy and so on. Essentially, the environment is going to kill the entanglement entropy, and then the dynamics becomes of Landau-Lifshitz type. But there are two cases when this is not allowed and not possible, which is S1 half and S1 antiferromagnet. So once you deal with this kind of materials, whatever we tried, it is not possible to kill their entanglement. Entanglement actually gets much worse and increasing out of equilibrium, and you cannot use LLG. So this is kind of the message of this slide. And why are we doing this? There has been an attempt to model nickel oxide using, let's say, TDDFT, but nickel oxide is also used in Stirling Colloidal community, and they never use any kind of single particle theory. They run very big guns on nickel oxide, DFT plus DMFT, Hubbard model, and stuff like that. We actually did try to describe nickel oxide with two-band TJ model plus proximity-induced coupling. You can get all kinds of complicated spectral functions now rather than band structure, because spaghetti band structure is gone. If you fire a laser pulse, you see immediately that this kind of quantum system increases entanglement entropy, not going to zero. So that would make it even more difficult and nearly impossible to apply anything close to LLG. And it does radiate, and this is like the final message of the talk. It does radiate, but not in terahertz. It just radiates 0, 2, 4, 6 high harmonics. So we are still working on this problem. That's why not published. But just showing that if you do want to model nickel oxide for the purposes of this terahertz Spintronics experiments, you would have to shift to many-body physics of strongly correlated models like Hubbard model. Okay, so this is my conclusion. I am 3 minutes past the 10 a.m. in the US, and I welcome any questions.
Thank you. Okay, I'm sitting an applause for you. Okay, great. Let's see what. So let's see. Sumit. Let me promote them to panelist, and then also there. They'll join us in a minute. Yeah. So Sumit, go ahead and ask your question if you want to unmute yourself. Yeah.
Hi, Branislav. How are you doing?
Hi, Sumit. Yeah,
nice talk. Thank you. I have a question about the dissipation mechanism you have here. So if I understand correctly, you have one dissipation mechanism through this jumping operator in your Lindblad formalism. And also, let me finish it. I think in the very beginning, when you describe this.
Yeah, so by the way, this in this situation, semi-infinite lead takes care of dissipation because of continuous energy spectrum. This is a kind of big secret embedded into the structure of quantum statistical mechanics. Kubo formula operates like that as well. You can only use Kubo formula on infinite systems, rigorously speaking. In this case, once you put continuous energy spectrum to the semi-infinite leads, what you really see is that you apply some bias voltage and everything becomes steady state. Even though you're not modeling phonons, it's a kind of fermionic bath, if you want. In the previous example, when I was doing the light-driven MN3 ascent, I cannot put the leads because nobody has leads in those experiments. So it's just like isolated two layers, you know, sitting in some experimental equipment. But if I do not dissipate, I would have currents flowing forever because it's a closed quantum system. Closed quantum systems, they continue dynamics until the end of the universe. And that's, of course, unphysical. And so one of the catches of using this, we actually used exactly the same quantum master Lindblad jump operators as were used in the New Journal of Physics by Toppler, Henk, and Mertig. But they were defining the jump operators on a technical level, and you had theories, I'm going into these details, in the basis of equilibrium energies and eigenstates. And that turns out for us not to do the all currents go to zero. So we ended up diagonalizing Hamiltonian, that's why we have these pictures here, at each time step. And then the dephasing was done in the instantaneous eigenbasis. And only when we did that, we were able to bring all the currents to zero sometime after the laser pulse ceases to exist.
Okay, great. Peter, why don't you please tell us the next question, Peter?
Yes, hello, Branislav.
Hi, Peter, yeah.
Thank you for a very nice talk. I was wondering about the first part where you had Yerfimenko's equation, you had Lindblad's equation and LLG. It was quite in the beginning.
Yeah, this.
Yeah, okay, yes, here it is basically. And I was wondering about the approximations, because if you go to the LLG, and maybe it was in some later part of your talk, but the LLG assumes that everything is transversal. So what it means is that the moment cannot do a longitudinal relaxation.
This is excellent.
Conserves the moment, but the Lindblad equation would not do that.
Excellent question, yes. And you know, this is the if you look at the standard LRG equation, these guys are unit vectors of fixed length, unless you shift to Landau-Lifshitz-Bloch equation, but this is something else. And there is a very new derivation which I'm kind of advertising, which have advertised already. This is a derivation of LRG equation, in which we start from quantum fields for localized magnetic moments and electrons. And then we remove in the Schwinger-Keldysh formalism the quantum fluctuations, then deliberately make them, you know, classical. And then we arrive at a standard LRG equation with some non-local damping. It's a kind of like deepening of all the stuff you have in your papers, but without having the spin-orbit coupling at all. But I do have, you know, a bunch of papers which discuss exactly this. So this is like another talk on quantum spin transfer torque. So what happens in all of these papers is exactly what you're saying. So if I switch to fully quantum description of localized spins, then the presence of entanglement, which has to be zero for LRG to be valid, once the many-body states of the magnet, which means you have ket up, 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 plus ket up, down, up, 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 and so on. Once you generate this kind of stuff on the quantum level, you will see shrinking of the spin. And you can even have, if you take a look, I didn't have a kind of time at the end of the day, but now it's a question answer session. You see that on the top of the slide, and by the way, the things from the Zoom, so I don't even see what you see. On the top of the slide, I mentioned non-classical magnetization dynamics. So in this problem of this TJ Haber type model hit by light, the only dynamics I see is the one you are mentioning. I only see this.
Right.
I only see magnetic moment going up and down. And by the way, in electrodynamics, that would radiate. But that does not exist in any classical micromagnetics, because you have a vector which is changing length, but it doesn't rotate. And in some of these papers on the quantum spin torque, which is again a topic of a completely different talk, you would see that kind of dynamics. Magnetic moment changing length, but never rotates away. And this is exactly the realm of problems in which you would have to give up on using the LNG. So as I said, right now, we have checked many of the examples of different environments hitting magnets, and we do find some of them having non-zero entanglement entropy. And once you have entanglement, expectation value of spin operator in entangled state is not going to be the same. It depends on the degree of entanglement. The more entanglement you have, the smaller the expectation value. The most conspicuous example of that type is antiferromagnet, the quantum spin liquid. In that case, the entanglement is so strong that you have zero. There is no any kind of magnetic moment. And this has been, by the way, recently even observed experimentally by measuring this witnesses of entanglement. So yeah, so you're completely right. There would have to be extra work to take that kind of dynamics.
Thank you for the answer.
Thank you.
Sumit wanted to follow up on that.
I think Sumit would like to follow up because Ali Reza, I think it was you. Peter took his question, so go ahead. Go ahead, Sumit.
Thank you, Ali, for surrendering your question. I have a question regarding, again, the dissipation itself. So if I go through this Lindblad formalism, it is essentially a Markov process. So you don't need any memory or past time. But at the end, you show the derivation when the kernel depends on the time, right?
You mean kernel of LG equation?
Yes.
That would be like, so yeah. So throughout the talk, I was using two different quantum electrons plus classical localized magnetic moments formalisms. In the first one, which is this one, I'm using Lindblad master equation coupled to some bosonic bath, electrons coupled to bosonic bath. In the second one, it is this electronic subsystem that generates time retarded damping in the LRG equation effectively once you integrate them with each other. And we see that right now, like we are really confident that this result is there because we saw it numerically, and now we have analytical proof of the same thing, and the two results match completely. And this will be this new paper on Schwinger-Keldysh. So electronic system does introduce memory into the LRG equation. Like how important is memory? Usually you can expand these kernels and keep only the lowest terms. And if you do that, you would get dm over dt, which is damping, and you would get Peter Oppenheimer's inertia. So usually you don't keep the kernel. You only expand the kernel up to some order, and you keep the two terms that are studied experimentally, which is damping and inertia is d square over d square or m over dt square. So in other words, if you have these electrons which can flow in and out of the system as the bath, they can generate magnetic inertia, something we discussed a few months ago exactly in this forum, on the magnetization, even without spin-orbit coupling. Because in Peter Oppenheimer's theory, I think spin-orbit coupling is sine qua non to have the inertia. But this is another method, Having a bath means they come, interact, and then go away into some reservoirs. So that process of going away into the reservoirs can generate inertia as well. Okay. Second term in the expansion of that kernel that you're asking about.
I think Peter wanted to follow up on the question as well.
I had another question, but let me first say that in the paper where we discuss inertia, we distinguish between intrinsic and extrinsic. So intrinsic inertia, spin-orbit coupling. But
Sure.
extrinsic, that could be something else, what you are mentioning.
Yes. And by the way, there is a new paper, nice paper by Dyne, in which they get, it even has in title, they get inertia from caldera-Leggett bosonic bath.
Yeah.
Interacting with ferromagnetic insulator.
Yeah. I had another question about the result if you use Giffey-Menko's equation. Yeah, and actually we also do that. So you can calculate the terahertz spectrum.
Sure.
Yeah, and what do you get? Because, and what is the main term? Because you have three terms for the E field. It is on the slide here. You have three terms. What is the main term? And what is the width of the bandwidth of the terahertz spectrum?
That's an excellent question, yeah. So we actually just working on that. I have some preliminary results, we could discuss it further. So according to current data, which is just from, this week, this term here, you see what is circled? Yeah. So that term generates 100 times bigger contribution to outgoing Terahertz radiation than the other two, these two. The term that is sometimes naively, but that's why you need a theorist, to help you, invoked this one here, which is like just a dipole moving, quantum dipole in this case, like spin origin. That one is like 4 orders of magnitude smaller than anything coming from the current. So the conclusion is that current is the most important, but there is actually also so this is like if you look at the total field, but if you look at the terahertz range itself, then this guy could give you something that is also relevant in the terahertz frequency range.
Okay.
So that would be my answer, but this is not something I was discussing at great length.
Okay. No, I agree with it. It is also what we find.
Okay, that's great.
Yeah, but often the calculated spectrum is too wide.
Oh, that's true. That's actually, yeah, it's too wide when compared to experiments.
Right.
But you can see it here. It's like 60 terahertz, 60. It's too wide. Yeah.
Much too wide. Okay.
Yeah, that's a very interesting question. Eventually, the proper one should not go beyond 30, I think.
In many cases, it's below 20.
Yeah, in experiments, yeah. Like in this original images I had, they don't plot more than, they plot like, they go up to 30 usually, 20, 30. Here is like 14, yeah. So you're right. We see that all the time that you do get terahertz in a much broader range than